So there are situations where you have some type of a function. This is clearly a nonlinear function. F of x is equal to 1 over x minus 1. This is its graph, or at least part of its graph right over here. But where you want to approximate it with a linear function, especially around a certain value. And so what we're going to do is we want to find an approximation. Let me write this down. I want to find an approximation for, and actually let me be clear, I want to find a linear approximation. So I'm going to approximate it with a line. I want to find a linear approximation of f around, and you need to know where you're going to be approximating it, around x equals negative 1. So what do we mean by that? Well, let's look at this graph over here. On this curve, when x is equal to negative 1, f of negative 1 is negative 1/2, which takes us right over there. Let me do this in a better color. So it's right over there. And what we want to do is approximate it with a line around that. And what we're essentially going to do is we're going to approximate it with the equation of the tangent line. The tangent line is going to look something like that. And as we can see, as we get further and further from x equals negative 1, the approximation gets worse and worse. But if we stay around x equals negative 1, well, it is as good as you can get for a linear approximation, or at least in this example, it is a very good linear approximation. So when people say, hey, find a linear approximation of f around x equals negative 1, or if they say, what is the following is the best approximation, and all of your choices are lines, well, essentially they're asking you to find the equation of the tangent line at x equals negative 1. So let's do that. So in order to find the equation of the tangent line, the equation of a line is y is equal to mx plus b, where m is the slope and b is the y-intercept. There's other ways that you could think about it. You could think about it in terms of point slope, where you could say y minus some y that sits on that line is equal to the slope times x minus the corresponding x1. So x1 comma y1 sits on that line someplace. And actually, I like to write this point slope form like this sometimes. Y minus y1 over x minus x1 is equal to b. Because this comes straight out of the idea of, look, if x1 and y1 are on the line, the slope between any other point on the line and that point is going to be your slope of your line. So we could think about it any of these ways. So let's first find the slope of the tangent line. And that's where the derivative is useful. So actually, let me just write f of x again. So I'm going to write it as x minus 1 to the negative 1 power, because that makes it a little bit clearer that we can use the power rule and a little bit of the chain rule. So the derivative of f with respect to x is equal to, so the derivative of x minus 1 to the negative 1 with respect to x minus 1, well, that's just going to be, we're just going to use the power rule here. It's going to be negative 1 times x minus 1 to the negative 2. And then we're going to multiply that times the derivative of x minus 1 with respect to x. Well, that's just going to be 1, right? The derivative of x with respect to x is 1. Derivative of negative 1 with respect to x is 0. So we could say times 1 here if we like. Or we could just not write that because it doesn't change the value. And so let's evaluate that when x is equal to negative 1. So f prime of negative 1 is equal to, I could just write this as negative, all right, like this way, negative 1 over negative 1 minus 1 squared. And so this is going to be negative 2 down here. So this is equal to negative 1/4. So the slope of our tangent line is, so I could write this way, m is equal to negative 1/4. And so now we just have to write its equation down. So we already know an x1 and a y1 that sits on the line. In fact, we want to use the point when x equals negative 1. So we know that the point negative 1 comma, we could just input it right over here, f of negative 1 is negative 1/2, 1 over negative 1 minus 1, negative 1/2. So we know that this -1 comma -1/2, that is on our curve and it is on our line. That's the point at which the tangent and the curve actually intersect. And so we can use any of these to now write the equation of our line. We could say y, I'll do it right here, y minus y1, so minus -1/2 is going to be equal to our slope -1/4. I'm just using the point slope version of our equation, is equal to our slope times x minus x1. So x minus our x coordinate that we know sits on this. So minus -1. And so let me now write all of this in a neutral color. This will be y plus 1/2 is equal to, and I can, so this is going to be plus 1 right over there. So I can distribute the -1/4. So it's -1/4 x minus 1/4, and then I can subtract 1/2 from both sides. So I'm going to get y is equal to -1/4 x, and then if I already am subtracting 1/4 and I subtract another half, that's going to be -3/4. So -3/4. So, and that's actually pretty close to what I drew up here. This should be intersecting the y-axis at -3/4. So there you have it. This line, or you could even say this equation, is going to be a very good linear approximation, about as good as you can get for a linear approximation, for that nonlinear function around x equals -1. You might say, well, why didn't they just ask me to find the equation of the tangent line at x equals -1? Well, they could have, but there's a little bit of extra cognitive processing here where you say, okay, I can actually use the equation of the tangent line to approximate this function around x equals -1.